Hello, this is Dr. Joe Trout from the physics program at the Richard Stockton College of New Jersey. In this lecture, we're going to talk about Chapter 4. We're going to talk about heat, temperature, and atmospheric circulation. First, let's look at the hottest and driest places in North America. Right, that's Death Valley. It's about 134 degrees Fahrenheit in 1913, and it's the second highest temperature ever recorded on Earth. In the summer of 1996, there was 40 successive days over 120 degrees Fahrenheit and 105 over 110 degrees Fahrenheit. The reason it's so hot here is because the topographic settings and the atmospheric circulation and the intense solar radiation. So in this chapter, we're going to talk about the causes and consequences of heat transfer within the Earth atmosphere system. We're going to discuss temperature and temperature scales, and talk about heat, how it's related to temperature, how it's transferred, and how it affects our atmospheric circulation. We know that all matter is composed of molecules or particles and are continuously in vibration, rotation, and translational motion. So for instance, we know we have the oxygen molecules, which are two oxygen atoms, and they're moving around in the atmosphere. As a rough model, you can consider this as being two softballs connected by a spring. And what happens is the molecules, when they become warm, start to oscillate back and forth with this spring. They also rotate like a tumbling barbell. And they move in a straight line. That's what translational motion is. This energy is called kinetic energy. It's energy due to motion. And it's equal to 1/2 times the mass times the velocity squared. Temperature is actually a measure of this average kinetic energy of the molecules. So temperature is directly proportional to the average kinetic energy of the molecules or atoms composing a substance. These substances and these atoms have internal energy. And when we talk about internal energy, that's going to count all of the energy in the substance. So it includes kinetic energy. It also includes potential energy arising from forces between atoms and molecules. For instance, we know that two positive charges repel, and if two positive charges are sitting next to each other, they have a potential energy due to this force between them, this repulsive force between them. Heat is just energy in transit. So when two substances are brought together with different temperatures or different amounts of kinetic energy, the energy is transferred from the warmer object to the colder object. That's what happens naturally. So if we have a warm object and a cold object in contact, heat will flow from the warm object to the cold object. We can make heat flow in the opposite direction. For instance, we can remove heat from the refrigerator, but this takes work to do. So for instance, in our refrigerator, we have an electric pump that pumps gases around, and we use this to remove the heat from the refrigerator. We'll talk about 3 temperature scales. The first one is Celsius, and the second one is Fahrenheit, and the third one is the Kelvin scale. In Celsius, how they got this scale was they took a fluid and put it in a tube, and they put that tube in ice water, and we called that 0 degrees, and they put a mark on the tube. Then they took that same tube and put it in boiling water, and we know that things expand when they get warm. So what happened is the fluid expanded, and when it stopped expanding, they marked that as 100. So we stick it in ice water, we mark off the 0 point. We stick it in boiling water, we mark off the 100-degree point, and then we put 100 marks in between. And that's where the Celsius scale came from. The Fahrenheit scale is also based on the melting point of ice, which is 32 degrees, and the boiling point of water, which is 212 degrees. It's also loosely based on body temperature. So we know that our body temperature is about 98.6 degrees. And the reason is because Fahrenheit wanted his temperature scale to be based on body temperature. The problem is, if he would have made body temperature exactly 100, then the melting and boiling points wouldn't be whole numbers. So it'd be something like 32.7 or something like that, and 212.3. So to make life easier, he made boiling 212 and freezing 32, and body temperature came out to be close to 100. The absolute, or the Kelvin scale, where we have absolute 0, is based on what happens if all molecular motion was to stop. So if the kinetic energy was 0. In table 4.1 we see the conversion. So for instance, if we knew what degrees Celsius were, so for instance, let's say it's 20 degrees Celsius, that's 20 divided by 5 is 4, times 9 is 36, so we get about 68 degrees. So 20 degrees Celsius is about room temperature, about 68 degrees. If we knew the degrees in Fahrenheit, we could plug it into the second equation. It's Fahrenheit minus 32 degrees times 5 and divided by 9. To get Kelvin, we just add 273.15 to Celsius. So once again, the Celsius temperature scale is based on the freezing and boiling points of water. The Fahrenheit temperature scale is also based on the freezing and boiling points of water, and it's also loosely based on body temperature. And finally, the Kelvin scale is based on the kinetic energy of the molecules, and we say at absolute 0 or 0 degrees Kelvin, all molecular motion would stop. By the way, when we use Celsius, we use degrees C, and we use Fahrenheit, we use degrees F. But if you're using the Kelvin scale, you don't use a degree sign. You just say 0K or 22K or whatever. The temperature scales measure a degree of hot or coldness. The unit of energy we use for heat is a calorie. A calorie is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. It's different from a food calorie. A food calorie is actually 1,000 calories or 1 kilocalorie. More common today, we'll use the joule, and 1 calorie equals about 4.18 joules. In English units, we use the British thermal units. This is the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. 1 BTU, or British thermal unit, is equal to about 252 calories, or 1,055 joules. How do we measure temperature? Well, you're probably most familiar with a thermometer, which is a liquid in a gas tube. And a liquid is usually either mercury or alcohol, and it expands when it gets warm. Another type of thermometer is called the bimetallic strip thermometer. And if you look in the thermostat for your heater, you'll see one of them. Here there's 2 strips of metal, and metal expands, different metals expand at different rates. So what happens is if you mount these 2 pieces of metal together, one of them will expand more than the other, and it will twist. There's also a thermometer that's based on the electric resistance. A thermograph is just a measures and records temperature according to time. The important properties are the accuracy and response time. So for example, the mercury thermometer doesn't react very quickly. Right? That's one of the reasons you have to keep it in your mouth for a while if you're measuring your temperature. The electric resistance thermometer reacts much faster. It's also important to have these thermometers, if we're measuring the temperature outside, to have it in a well-ventilated area, but yet it has to be shielded from the weather. A temperature gradient is how temperature changes over distance. So for example, there's a temperature gradient from the hot equator to the cold north and south poles. And heat flows in response to these temperature gradients. So heat flows from towards the lower temperature and tries to eliminate the gradient. So if you have a hot item and a cold item and you stick it together, heat will travel from the hot item to the cold item until they're both the same temperature, until they're both warm. Heat flows by 3 processes: radiation, conduction, and convection. Conduction is probably the easiest to explain. If I have a hot object and I stick it next to a cold object and they're touching, so they have thermal contact, heat will flow from the hot object to the cold object. So for example, if you have a cold ceramic coffee cup and you place hot coffee in it, the cup will warm up and the coffee will cool down. The second type of heat transfer is convection. And this is where we take a hot fluid and the fluid moves, taking the heat with it. So for example, that's how we get smoke to go up our chimneys. Right above the fire in our chimney, in our fireplace. The air gets hot, it expands, it becomes buoyant, and that hot air travels up the chimney. We also have radiation, and this is heat transfer through electromagnetic waves that we talked about in the last chapter. Most of the energy we get from the sun comes from radiation, right? We're not touching the sun. There's not a hot fluid which flows from the sun. In fact, there's a vacuum of space in between us. So the energy that we're getting from the sun, this heat energy, is coming in the form of electromagnetic radiation. There's two types of heat: latent heat and sensible heat. Sensible heat is any heat that changes the temperature of an object or a fluid. Latent heat is the heat required to change the phase, especially in water. So for instance, if we add heat to an ice cube and the ice cube melts, that heat is latent heat. If we have water and we add a heat to it and the temperature increases, that's called sensible heat. Radiation is actually both a form of energy and a means of heat transfer. So radiation will occur even in the vacuum of space. Anyone who's been camping where they've built a nice big campfire has experienced radiation firsthand, right? If you're standing some distance from the fire, we know you're getting warm. But we know it's not coming from conduction because you're not touching the fire. It can't be convection, because if you think about it, if it's convection, that heat is going straight up from the fire. So what's happening is you're getting radiation. The heat is radiating from the fire. And anybody who's done a lot of camping and has been near a fire that's really hot knows that if you're standing really close, the front of you is about to burn off and your back is freezing cold. So this is radiant energy. The way the energy reaches the earth from the sun is also by radiation. So when we absorb this radiant heat, it causes the temperature of the object to rise. So if an object absorbs radiation, it causes its temperature to rise. So it converts that electromagnetic energy to heat. If absorption is greater than emission, then we have radiational heating. If emission is greater than absorption, we have radiational cooling. So, if I have an object and it absorbs radiant energy, it heats up. Now it's starting to get hot and it radiates out energy. If what's coming in, the absorption is greater than the emission, we're heating. If the emission is greater than the absorption, then we have cooling. Conduction, as we said, is transfer of kinetic energy of molecules or atoms by collision between neighboring atoms or molecules. So for conduction, things have to be in thermal contact. The ratio of the rate of heat transport across the area is proportional to the temperature gradient. So some materials might have a higher heat conductivity than others. So in general, solids such as metals are better heat conductors than liquids, and liquids are better heat conductors than gases. Conductivity is impaired by trapped air. So for example, that's why fiberglass insulation works, and also why wetsuits work, and why a thick layer of snow will also insulate. So a thick layer of snow is a good insulator because of the air trapped between the individual snowflakes. As the snow settles, however, it starts to lose its insulating properties. So here shows the heat conductivity of a few objects, or a few substances. Copper conducts heat very well. That's why we coat our pans with copper. And aluminum and iron also conduct heat very well. Ice doesn't conduct heat very well, and dry sand does not either. Okay, stagnant air is a very poor heat conductor. Convection is a process where we heat the fluid and then the fluid moves. It's a consequence of the differences in air density. So what happens is the sun comes down and through radiation it heats the earth. Now the earth is hot. It warms the air just above it. So what happens? That air expands and becomes buoyant, and it moves up into the atmosphere where it cools. Then cold air comes in to fill in where that air was when it's getting warm. Okay, so we have the sun coming in through radiates, heats the ground heats the air, just like a hot air balloon. The air expands and it starts moving up into the atmosphere where it transfers the energy and it comes back down. So with convection, it's the consequences of differences in air density. The transport of heat within a substance via the movement of the substance itself. So we heat the air and the air moves. For this to occur, the substance must generally be either a liquid or a gas. Right? We don't talk too often about convective heat transfer to metal. This is a really important process for transferring heat in the atmosphere. So the convection cycle, we have ascending air, expands, cools, and eventually sinks back down to the ground. Water can absorb or release heat during phase changes. And this heat is known as latent heat. So for example, if we have warm water and we cool it to 0 degrees, it'll begin to turn to ice. During the transition period, the temperature remains the same. So if we keep taking heat out of the water, and this is the latent heat, what eventually happens is that water would freeze. So this shows the different things that can this graph shows the different things that can happen to water. It can start as a liquid, it can evaporate and become a vapor. So what happens is we added heat to the water and it became a vapor. So this vapor is steam. If we take heat out of the steam, it can condense and become water again. If we have water and if we reach 0 degrees and we take out more heat, it freezes, becomes solid. If we add heat to the ice, it'll melt. We also have something called sublimation. So this is when we go straight from a solid to a vapor. A good example of this is if you ever put clothes out on the line to dry. What normally happens is the clothes freeze and then the water vapor, the water that's frozen in the cloth, turns into a vapor. We also have deposition. This is where water vapor can turn directly into a solid without going through its liquid phase. The specific heat is the amount of heat required to raise 1 gram of substance 1 degree C. It's different for different substances. So for example, to raise 1 gram of water 1 degree C takes 1 calorie. But aluminum, to raise at the same temperature 1 degree C, only takes about 0.2 calories. And sand only takes about 1.88 calories. So this is important when we're talking about things like offshore breezes. So you might notice when you go to the beach this summer, if you go early in the morning, the sand is cool and the water's at some certain temperature. As the day wears on, around noontime, you notice that the sand is burning hot, but the temperature of the ocean probably hasn't changed much. This is due to the specific heat of the sand and the specific heat of the water. It takes much more heat to change the temperature of the water than it takes to change the temperature of the sand. This brings about something called thermal inertia, which is a resistance to change in temperature. If there's a large body of water, it exerts a greater resistance to temperature change. So for instance, in the spring, when the temperature is increasing rapidly, the temperature of the ocean isn't increasing as quickly. However, and also in the fall, the land is becoming colder and colder, where the ocean is taking a while to cool off. So this is known as thermal inertia, and the oceans have a greater thermal inertia than the land does. So for instance, in Atlantic City, when we had those bad winter storms this winter, it was actually much worse in Philadelphia because Atlantic City had this nice ocean next to it, and it had a lot of heat. It was still cooling off during this process. If we look at two cities that are at the same latitude, roughly, San Francisco and St. Louis, we see that if we look at the temperature of those cities over a year, we see that there's a big change in St. Louis, where in San Francisco, there's a much smaller change. So it's still cold in the winter, it goes to about 10 degrees, and in the summer it gets up to about 15 degrees C. Whereas St. Louis, the winter is about 0 degrees C, and the summer goes up to about 25 degrees C. San Francisco is near the water, or near the ocean, and St. Louis is not. We say San Francisco has a maritime climate, and St. Louis has a continental climate. So at the Earth's surface, we have absorption of solar radiation is greater than the emission of infrared radiation. And in the atmosphere, the opposite is true. We have an emission of infrared radiation into space is greater than the absorption of solar radiation. Therefore, the Earth's surface has a net radiational heating, and the atmosphere has a net radiational cooling. But the Earth's surface transfers heat to the atmosphere to make up for this loss. So this is what it looks like. Let's say we have 100 units of energy coming in, and it comes into the atmosphere. About 7% is reflected by the air, straight back out into space. About 16 units, or 16%, is reflected by the clouds. And about 8% is reflected by the surface of the Earth, or the surface of the, it could be the surface of a lake or the ocean. About 17% is absorbed by the atmosphere directly. So it's absorbed by water vapor, dust, and ozone. About 3% is absorbed by the clouds. The other 49%, so almost half of the energy, makes it through the atmosphere and hits the Earth's surface. This warms up the Earth, and now the Earth starts re-radiating back out. So what we have is about 114 units, or 114% of the incoming, is re-radiated out at a longer wavelength. 105% of that is absorbed by clouds, water vapor, CO2, and O2. They get warm and they radiate energy back onto the Earth. If you notice, 49 plus 95 gives you about, gives you a 144. We also have sensible heat flux. This is heat that causes a temperature change, and latent heat flux. So this is about 7% and about 23%. So that makes up for the extra 30%. Now the atmosphere is warm, it re-radiates out into space at a long wave length, and this is about 40 units, or about 40%. And the clouds become warm, and they also emit long wave radiation into the atmosphere, or back out into space. So we assume that this is pretty much an equilibrium. As much heat that's going in equals the heat that's going out, or the energy that's going out. So if you notice, 7 plus 16 is 23, plus 8 is 31, plus 9 is 40, plus 40 is 80, plus 20 is 100. So we have 100 units coming in, and we have 100 units going out. If there's more coming in than going out, then we must be warming up. And if there's more going out than coming in, we must be cooling off. But roughly, we assume that this is to be in equilibrium, so the amount coming in equals the amount going out. All right, so this is just another table saying the same thing. All right, we have 100 units coming in. Scattered by and reflected to space is about 31. Absorbed by the atmosphere is about 20. Absorbed by the Earth's surface is 49. We end up with 100. If we look at the infrared cooling, it's about minus 19. And the solar heating is about plus 49. We end up with plus 30. If we look at the atmosphere, the cooling is about minus 50. The heating is about plus 20. We end up with minus 30. And finally, if we look at the non-radiative heat transfer, so this is sensible heating and latent heating, that's about 30 units. So latent heating. Some of the absorbed solar radiation goes into vaporizing water at the Earth's surface, and this energy is released into the atmosphere when clouds form. So large amounts of heat are needed for phase changes of water compared to other substances. This is a graph that shows what happened. Let's say we take a chunk of ice that's colder than 0 degrees, and we go ahead and we start to add heat to it. And if we go ahead and start to add heat to it, what will happen is we'll warm up the ice. When the ice gets to 0 degrees, it'll begin to melt. During that phase change, the ice and water mixture will stay at 0 degrees. So if you've ever taken a chemistry lab or a biology lab, that's why we use ice baths, because we know that the temperature will stay at 0 degrees as long as there's some ice there. The instant that the ice is gone, it'll begin warming up if we keep adding heat. And we keep adding heat till it gets to 100 degrees. Once that happens, if I continue to add heat, that water will turn to steam, so it'll boil and turn to steam. And during that process, this boiling water will stay at 100 degrees until it's all steam. And then we can heat the steam if we capture it. Notice that our X scale here is the calories of heat we added. Notice that it doesn't take much heat to warm the ice. It takes a significant amount of heat to change the ice into water. But look at how much energy it takes to change the water into steam. Right, so roughly this is 200, this is close to 800, it took about 600 calories per gram. So the melting takes about 80 calories per gram, where the evaporation took about 540 calories per gram, if we do a little more exact of a measurement. So at the Earth's surface, we have latent heating, and we'll have water becoming steam. Once the Earth is warmed up, it'll begin radiating out energy, and we say this is about 19 units, or about 38.8%. For sensible heating, that's where we have heat transfer, and the heat involved causes a temperature change. We say it's about 7 units, or about 13%. So heat transfer via conduction and convection can be sensed by a temperature change. And that's why we call it sensible heating. And it can be measured by a thermometer. Sensible heating in the form of convectional uplifts can combine with latent heating through condensation to channel heat from the Earth's surface into the troposphere. So this forms cumulus clouds. So what happens is we have warm, moist air, we heat it, it expands, it becomes buoyant, moves up into the atmosphere where it cools and condenses and forms clouds. We have a measurement called the Bowen ratio, and this describes how the energy received by the Earth's surface is partitioned between sensible heating and latent heating. So the Bowen ratio is the sensible heating over the latent heating. At the global scale, it's about zero point 0.3. So it's about 7 units for sensible heating and about 23 units for latent heating. So it comes out to be about 0.3. If we look at the land, we're going to have more sensible heating than latent heating because there isn't much water around. And we see the Boeing ratio is large. If we look at the oceans, we're going to have much more latent heating because there's a lot of water around and less sensible heating, so it comes out to be about 0.1. So the Bowen ratio measures this ratio. So what happens? We find that if we look at the tropics versus the middle latitudes, right, we've seen how in previous chapter how the Earth's surface is unevenly heated. So in the tropics, we get a more direct sunlight. And up at the poles, we get more indirect sunlight. So this causes a temperature gradient resulting in heat transfer. So the heat transfer moves from hot air to cold air. So it moves from the equator towards the poles. This is brought about through an air mass exchange and through storms and through ocean currents. So all that really hot air and all that heat that's been absorbed at the tropics, at the equator, will travel poleward where the temperature is cold. So we have heat transfer by air mass exchange. So of course we have a north-south exchange of air masses where we transport sensible heat from the tropics into the middle and high latitudes. We also have heat transport by storms. So tropical storms and hurricanes are greater contributors to poleward heat transport than the middle latitude cyclones. We also see heat transport by ocean circulation. So this contributes via wind-driven surface currents. And once again, what we see is that we have hot water near the equator and cold water near the poles, and we're going to get heat to flow from the hot water to the cold water. This shows how the Gulf Stream follows along the east coast, where the redder color is the warmer water. So why do we have weather? What there is that imbalances in radiational heating and cooling create temperature gradients. And these gradients are between the Earth's surface and the troposphere and between low and high latitudes. So we know at the Earth's surface it's warm, and as we go up through the troposphere, the temperature decreases. We also know that near the equator it's warm, and as we move up from the equator towards the poles, it gets colder. This cause and effect chain reaction starts with the sun and it ends with weather. So some of the radiation, the solar radiation is absorbed and converted to heat, and some is converted to kinetic energy. And this kinetic energy comes in the form of winds. So winds are caused by this kinetic energy, as well as the convection currents in the north-south exchange of air masses. So we see this rate of heat redistribution varies by season. So this causes the seasonal weather and the air circulation changes during those seasons. We also have radiational control, so the variation of air temperature is controlled by this radiational cooling or heating, and the factors that affect local radiation budgets and air temperature. And those factors are the time of day and the time of year. So of course we're absorbing more radiation during noontime and less during the sunrise and sunset. It's also controlled by cloud cover. So if we have a lot of clouds, then the surface isn't going to heat up so fast. And also due to surface characteristics. So as we said, the sand heats up much faster than the water does. So the annual temperature cycles represents these variations, and the annual temperature maximums and minimums do not occur at exactly the max and min of the solar radiation, especially in the middle and high latitudes. So for example, if the sun is most directly overhead at noontime, and yet it isn't noontime that we get the hottest weather, we get the hottest temperatures, right? It's usually a little bit past noon. So the atmosphere takes time to heat and cool. So the average lag time in the United States is about 27 days, and it can be up to 36 days with the maritime influences. So, for instance, Atlantic City isn't going to heat up as fast in the summer, and it's not going to cool off as fast in the winter. We of course have a daily temperature cycle. So the lowest temperature occurs just after sunrise, and the highest temperature usually occurs in the early to mid-afternoon. Dry soil heats more rapidly than moist soil, and less energy is used to evaporate the water if little water is present. More energy is therefore used to warm the earth and consequently the atmosphere. Relative humidity, which is the amount of humidity, the amount of moisture in the air divided by the amount of moisture that the air can hold, is also going to affect this ability for evaporation to occur. So, if we look at insolation, so the sun rises at about 6 o'clock and it sets at about 6 p.m. What's going to happen is the sunlight comes in, it turns on at 6 o'clock, it starts to warm the earth. Eventually, the earth starts getting warm and it starts re-radiating out energy. So what happens? Just before sunrise, we reach our lowest temperature. Then we begin to warm up. During this period, in the pink, there's actually a surplus of energy, and we continue to warm. In the afternoon, the sun's starting to set a little bit. The earth is still warm, so we're still radiating out energy. But now, the amount of energy coming in from the sun is starting to decrease. So this blue area shows where there's a deficit. So just before sunrise, we reach our lowest temperature. Just past noon, we reach our highest temperature, then we start cooling down, and this continues day after day. This annual temperature cycle decreases as we go up towards the pole. So for instance, if we look at Brazil, we're really close to the equator, and the temperature doesn't change much. This is the monthly mean. If we look at Kansas City, we're at about 39 degrees. Our winters are at 0. Our summers are at about 25 degrees C. And finally, if we look at Canada, this is about 62 degrees north. Our temperatures in the winter is about negative 30, and we go up to about 10 degrees C in the summertime. But as we move away from the equator, this change from winter to summer becomes more extreme. So why is it so cold when snow is on the ground? Well, first, snow has a relatively high albedo, so it reflects a lot of the energy that comes in. So that means that there's less energy absorbed by the surface and converted to heat. The snow also reduces sensible heating of the overlying air, so some of the available heat is used to vaporize the snow, not heat the air. Snow is actually an excellent infrared emitter, so during the night the radiative cooling effect of the snow is extreme, especially when the skies are clear. And cooling can be enhanced if there's light, winds, or calm conditions. When we look at the variations of air temperature, we can also talk about the cold and warm air advection. So this is air mass advection. This is horizontal movement of an air mass from one location to another. So for cold air advection, we have horizontal movement of colder air to a warmer area. Okay, so maybe from Canada down to the United States. Warm advection is where we have horizontal movement from a warmer air to a colder region. So maybe from the southern United States to the northern United States. The significance of this air mass advection to local temperature depends on the initial temperature of the new air masses and the degree of modification the air mass receives as it travels over the Earth's surface. So here, arrow A shows you cold air advection, and arrow B shows you warm air advection. Notice these lines are called isotherms. They're lines of constant temperature. Where these lines are close together, there's a strong thermal gradient. Where these lines are far apart, there's a weak thermal gradient. We of course also have man-made influences. So for example, the urban heat island is an example of a man-made effect. What we see this is that the urban heat island is a city of warmth surrounded by cooler air. So for instance, if we go to Philadelphia, we'll see that there's a relative lack of moisture in the city. And there's more available heat from absorbed radiation, and this is used to raise the temperature of the city surfaces. Because there's not much used in evaporation of water because there isn't much water. The greater the concentration of heat sources in the city, so cars and air conditioners and the such. There's also a lower albedo of city surfaces, so concrete doesn't reflect solar energy very much. It absorbs it. Also, building materials conduct heat more readily than soil and vegetation. So this develops best on nights when the air is calm and the sky is clear. So that ends our lecture today. So what we talked about were the different temperature scales. So we had Fahrenheit, Kelvin, and Celsius. And we talked about the methods of heat transfer, conduction, convection, and radiation. And we discussed processes such as moving latent heat processes where we change the phase of water, say from ice to water or water to ice. All right, thank you.